Look at this digital barrier. It represents your automated tests. AI test generators can build it in seconds, outputting hundreds of scenarios. But watch the anomalies. They slip straight through unseen microscopic cracks. These anomalies represent the specific edge case bugs that consistently leak into production environments. High test coverage metrics mask this vulnerability. A coverage count verifies that a scenario exists for a feature, but it fails to confirm if the scenario tests the exact conditions under which the feature breaks. Left to default settings, AI prompt outputs skew heavily towards shallow, happy path variations. Over the next 5 minutes, we will assemble a custom, project-specific prompt using the ICSR framework: instructions, context, skills, and rules. This method constrains the language model to generate scenarios at the exact boundaries where software fails. Before we begin building, gather 3 items. You will need access to your team's preferred AI tool, an exact API specification for a single feature, and a list of the last 5 defects that leaked into your production environment. Fixing defect leakage requires a structural shift in how we ask for tests. We will compel the AI to generate scenarios focused on boundary depth instead of simple volume. Step 1 dictates the rules of our framework. Open your team's bug tracker and retrieve the last 5 production defects that slipped past your QA process. An AI model generates outputs based on generic training data. It will never spontaneously test for your application's unique architectural quirks, like how your specific authentication service handles concurrent requests, unless you require it to do so. This table is the defect mining template. Use it to categorize your historical bugs. Map each defect ID to the exact scenario that would have caught it, and then assign it a broader failure category, like expired tokens or concurrent session handling. Take these final categories and write them directly into the rules section of your prompt. Instruct the model to generate at least 2 scenarios explicitly testing each of those historical failure modes. This process takes the accumulated implicit knowledge of your QA engineers and converts it into a hard constraint. The AI must now check every new feature against your team's specific history of failures. Step 2 builds the context. Delete any plain English descriptions of the feature from your prompt. Replace them entirely by pasting in your exact OpenAPI specification or database schema. When you describe a login endpoint with a summary, you force the AI to fill in the blanks using patterns from millions of other applications. It generates tests for error codes your API does not return and state conditions your application does not possess. This split-screen comparison illustrates the mechanical difference. On the left, vague feature descriptions produce hallucinated field names derived from general training data. On the right, providing the actual API contract yields accurate, context-grounded fields that match your project exactly. Enforce this by appending a strict directive to your context block. State exactly: generate only scenarios that reference fields, endpoints, and error codes defined in this specification. Grounding the model with a hard contract changes the operation entirely. The AI transitions from a generic recall task into a strict reading comprehension task based entirely on provided facts. Step 3 injects specific skills into the prompt. We start with the mathematical rigor of boundary value analysis. This technical number line represents a valid input range from 1 to 100. You must dictate exact numeric instructions in your prompt. Require the AI to generate scenarios at the minimum valid value, the maximum valid value, 1 below the minimum, 1 above the maximum, and 0. We apply this same strict logic to enumerated lists using a technique called equivalence partitioning. As the number line shifts into a drop-down menu structure, require the AI to select exactly 1 valid category in green and 1 explicitly invalid category in red. This prevents the model from generating redundant tests for the same valid state. Most engineers skip this and simply ask the AI to generate comprehensive tests. That phrase fails because the model's definition of comprehensive is based on its training distribution, which favors simple, successful variations. Dictating exact mathematical limits compels the AI model out of its default happy path bias and into true edge case territory. In our final assembly phase, we begin with the instructions directive. Open your prompt with a clear role definition, such as act as a QA engineer.
This quadrant graphic shows the completed ICSR framework. Combine your clear instructions, your contract-grounded context, your mathematical boundary skills, and your historical defect rules into one unified master prompt. Execute the prompt. Once the AI outputs the scenarios, you must immediately pivot to a mandatory human QA audit. This checklist displays the 3 specific questions for your audit. Verify that every referenced field matches your API documentation exactly. Check that the numeric limits strictly adhere to your boundary rules. Finally, confirm that these generated scenarios would have caught your 5 historical defects. The ICSR framework produces higher quality scenarios, but it does not guarantee perfectly correct tests. A QA engineer reviewing the output against the application's actual behavior remains an essential part of the process. You have now generated a robust, deeply detailed list of edge case test scenarios that map directly to the realities of your specific project. Structuring the prompt this way eliminated hallucinated API fields, mathematically covered your numeric boundaries, and incorporated known historical failures. Save this newly created ICSR template in your team's internal wiki. Mandate its use for every feature in your next development sprint to systematically drop your defect leakage rate.